Here's the lab setup for the energy conservation or ramp activity. In an ideal world, if you had a frictionless ramp, the potential energy of the disk at the top would match the kinetic energy of the disk at the bottom if we assign this value at 0. If I say the potential energy is 0 at the bottom, then all this change, the change in potential energy going from here to here, would all turn into kinetic energy. Turns out in real life you lose some to friction, and that's what this lab is going to work on. Your measurements you'll have in your lab notebook. You'll have the exact variables. You'll see that later how they're labeled. But my height is from the floor to this mark. That's my H0. My H1 is from the floor to this mark, and my H2 is from the floor to this mark. And what we're interested in is the change. So you do some subtraction and you find the vertical height from this mark down here to this mark. You'll also need the distances, what we call the delta x distances, from the first mark to the second and from the first mark to the third. We want to always start with the first mark because my initial velocity is 0, and as we know, if my initial velocity is 0, I can use the average velocity to find my final velocity. So in this video that I'll start right now, that's the first thing I'm doing. I'm measuring the distance from here to here and from here to here. I actually measured it there, and then I measured this part. Of course, you can add those two together. But you need the total distance from the first mark to the last mark. So you have to measure those distances. And then here I'm measuring the height from the floor to this mark, the floor to this mark, and the floor to this mark. When I get to this stage of the lab, I've already measured the mass. I've already had the map, figured out what the mass of the air disk is. Now I've turned the air on. And again, to get the time as accurate as possible, if you use a meter stick and you exaggerate pulling it away, it makes it much easier to know when you're starting. And then we've done this before. I'm just going to measure. You'll want the time it takes to get to this mark and this mark from the front edge. And then from that data, that's really the only data we have to collect. You don't need angles in this lab. There are going to be three different setups of 2 boards each. So 2 different groups can work on the same setup. So if they're going to have 3 different heights, it's going to have a ramp that's not very high, medium height, and a little higher. So that's the plan of how we're going to do that. So now you can take a look at the notebook. This is your energy conservation and ramp activity notebook entries. We have a diagram that matches the physical setup we've already looked at. We have our distance down the ramp, delta x1. The x's are always measured from the beginning. That way we can have our initial velocity 0. So delta x1 is from the first to the second tape mark. Delta x2 is from the first to the third tape mark. Your heights you measure from the floor that you enter in. You have h0 is your initial height, h1 is for the first tape mark, h2 is for the second tape mark. Then your delta, your change in height, is just you subtract where you're starting. You actually subtract the H1 height from the H0 and the H2 height from the H1. It's fairly, you guys can figure that out. The formulas we use are change in potential energy is mg times the change in height. If we just use that formula that way, we don't have to worry about where the potential energy is 0, because all we really are concerned with is the change in potential energy. We also really only want the change in kinetic energy, but since the disk is not moving at the beginning, it's 0. So if I find the kinetic energy here, that is the change because I started at 0. Same thing here. The change in kinetic energy is just equal. I can just use this formula. I have a total energy, which I call TE, and this should be the change in total energy. There should be a change there. Is equal to the change in potential energy minus the change in kinetic energy. That should be 0. I should not have any loss in total energy. In fact, I'm going to put the delta in there right now. So your change in total energy should be 0 if you had no friction, but we're going to have some friction in our system. These formulas we've used forever. Since our initial velocity is 0, we can use these combination of these 2 formulas to find the velocity here, which is v1, and the velocity here, which is v2. You can see I messed up originally. The percentage of efficiency is 1 minus your lost energy over your input energy. So if I lose 20%, my efficiency would be 80%. So I kind of forgot that and messed up, so I had to put the 1 minus in there. So we're going to take our change in total energy. So look at this. If you had a frictionless system and your change in total energy was 0, then this would be 0, and I'd have 1 times 100, which would give me my percentage efficiency. So it really should have parentheses around this whole thing before you multiply by 100. So you take how much you lose, the percentage you've lost from 1 and times 100, the fraction that you've lost from 1 times 100, and that gives you your percentage efficiency. It's just a little different way to look at it, and it was easier to calculate if we did it that way. So I actually did this lab, and these are the numbers. I measured my mass, my heights, and I measured my time and distance here. This is all one table, okay? It's not like these are not separate trials. This is all one. It just won't fit in one row. So my delta H1, I just subtract the two heights, and I got that. I use my formula for the change of potential is mass, G, and height, my change in height, and that gave me my 0.49, and that goes right there. And you guys, I think, can follow this. Again, this is just delta X over delta T, which we've used before. So that gives me 0.75 meters per second. I double that, and I get 1.5 meters per second. My change in kinetic energy is 1/2 the mass times the velocity squared. And again, since we've already put our formulas up there, I'm not going to make you rewrite them. We're just going to plug them in. And so I only got 0.41. Ideally, with no friction, it would have matched this. So I found my change in total energy. If you switch the order, it doesn't matter. We don't care if it's positive or negative. We just want to know how much we lost. We know it's going away, and I got 0.08. Then I just repeated the whole process for the second tape mark, and you can follow that on your notebook. And then your percentage efficiency. You can notice I originally had 16%. I wasn't thinking that's the percentage that I lost, so that means I kept 84%. And the same thing here. Notice in my situation, my efficiency went down the longer it went, and you might want to think about whether that makes sense. I'll be interested. I thought I would get a higher efficiency than this. If you're on one of the whiteboards, you may get higher efficiency, so we'll see how that works. I did my lab on the rough particle board. Good luck.